Good morning. We are making a video today about inverse trig functions and how to use them to solve equations. So the first thing we have to remember is kind of like what a function is. You know, functions are machines that do stuff. And functions have an input and an output. And we know that an equation is a function if one input gives us one output. And we should know that sine, cosine, and tangent are functions. And the reason they're functions is because the input for a trig definition is an angle. And the output is a ratio. So let's say we're talking about sine for a second here. And the question would be, how come the sine of an angle is always the same? And the answer comes from geometry in terms of, let's say we have this angle. Let's say it's like 25 degrees. If I make a right triangle there, the ratio of the height to the hypotenuse is going to be the same for that triangle as it is for this one. Because if I drop another perpendicular here, I have two angles the same. I have two similar triangles by angle-angle similarity. I could prove that these angles are the same by subtracting from 180, or by knowing that these are parallel lines and these are corresponding angles. Similar triangles imply proportionality, and proportionality means equal ratios. And that's why any angle gives me the same ratio. And so sine is a function. Now, one thing we've learned before is inverse functions. And we know how we can tell inverse functions. Like if we make a sine graph, this red graph, then we could do the vertical line test to see that, oh yeah, it only intersects in one place, and so it's a function. But what we also figured out is that we could do a horizontal line test to see if it's a one-to-one function, and it isn't. Meaning, for a function, one input generates one output. For a one-to-one function, one output also generates one input. And so only one-to-one functions have inverses. And so we would say that sine doesn't have an inverse. And yet, our calculator has this button on it, sine -1, which is an inverse button. And sure enough, we've been using inverses for a long time to find angles. Now, if you graph the inverse sine, or the arc sine, on a computer or a calculator, you will often see that it actually limits it. See this blue graph? Like it's stopping the graph. Really, if I kept going, what I would get is, of course, our sine graph rotated around the xy axis. But it stops it here and here. And the reason it stops it here and here is because as soon as it continues past those points, then all of a sudden you're talking about a line that's a graph that's going to fail the vertical line test, and it's not going to be a function. Computers don't deal very well with relations that aren't functions, so it limits it on purpose. So the blue line is the inverse of sine, but limited so that it's a function. One thing we know about inverse functions is that x and y switch. So for sine, the inverse of sine, if the input of sine is an angle and the output is a ratio, when you're using the inverse, you're putting in the ratio and you're getting out an angle. But if that's true, then what is also true is that domain and range will switch. So the domain here is really any angle, right? And the range is that sine is less than 1 and greater than or equal to -1, because the hypotenuse of a triangle is always the biggest. Well, what that means is that the domain of the inverse function should be between 1 and negative 1 for the same reason. But the range really can be anything. And if we look at our graph, that is definitely true. You could see this is stopping at negative 1, and this is stopping at 1. It doesn't go past that. Because if I tried to say that the sine of an angle was 7, you would say that's crazy. Because that would mean that one side of the triangle was 7 times as large as the hypotenuse, and that's not going to happen. So the limitations of the y values on the function become the limitations of the x values on the inverse function. Alright, so that's it in general. Now let's talk about how we use it. So what we need to know is that it's kind of like logarithms. We know, for example, that if I do log 2, 8, we would call this, we've called it in class, that this is an exponent finding machine. This is asking, exponent finding machine, this is asking what exponent would I have to put on 2 to get to 8? And of course the answer is 3. But what that means is that this represents an exponent. And inverse sine is like the same thing. It's cosine tangent. Same. So if I have the sine, the inverse sine of, let's say, I don't know, 2/3, what I have to understand about this is that this is an angle finding machine. And if it's an angle finding machine, then anytime I see it, I need to recognize that it means that this represents an angle. That's an angle. Alright. You know, some days you come in and you want to get a time done and the technology just gets in your way. So, 2 hours later, we'll pick up where we left off. We're going to run through some problems involving inverse trig functions so that you can see how you can use them. Here's an example. Let's say I wanted to take the tangent of the inverse sine of 3/5. The important thing to understand is that because this is a angle finding machine, this is really the tangent of an angle. Which angle, you might ask? Well, it doesn't really matter. The reason it doesn't matter is because we can just call it angle theta, for example. If we know that the sine of something is 3/5, then we know that the y value is 3 and the r value, or the hypotenuse, is 5, since this is an r value. So 5, 3, you can use Pythagoras to find that the x value is 4. And so the tangent of that angle must be 3/4, y over r. You're finding the tangent of an angle, therefore you will only get one answer. Contrast that with a different type of problem where you're looking for angles. So, if we go from the angle to the ratio, each angle generates just one ratio. If you go the other direction, and you have the ratio and you're looking for an angle, there are so many angles that can make the same ratio, you're going to get really an infinite number of solutions. Here's an example. Let's say I have the inverse cosine of √3/2. So I know that √3 would be an x value and 2 would be an r value. I'm looking for an angle. So I could draw a triangle on a coordinate plane. I could put a √3 in and a 2 in. And I'd probably recognize pretty quickly that that's a 30, 60, 90 triangle. Hopefully by now, I'd also know that's pi over 6 radians. Because if pi is 180, 180 divided by 6 is 30. Therefore, pi over 6 is unanswered. It seems like the answer, but it's really unanswered. And the reason it's unanswered is because there are a bunch of angles that can make that blue triangle. For example, there's this blue angle, but there's also, what if I went in a whole circle and came back to here? I'd still get a 30, 60, 90 in the first quadrant. So, long story short, any coterminal angle is going to make the same cosine, which we know. And so I could say that pi over 6 or any coterminal angle would make √3/2. So I'm going to say pi over 6 plus 2 pi k, where k is an integer. If it's a whole number, it represents a whole circle. I've gone in a circle, I end up in the same place. But also, There's another place that could make root 3 over 2. In fact, there's kind of always 2 per circle, because cosine is positive here, negative here, and positive here. That means I could make this same 30, 60, 90 down here at negative pi over 6, and I would still get root 3 over 2. And so I have to say it's not just pi over 6 plus 2 pi k, it's also negative pi over 6 plus 2 pi k. That represents an infinite number of angles that all have a 30-degree angle of reference on the positive side of the y-axis. Alright, what else we got? We did that one. How about this one? We're going to express this algebraically in terms of a. Now your book uses x there and x there. I don't like using x there. They're using it as sort of like, y equals x. It's like a functional type of thing, but it's confusing because when we try to draw things out, we have x values and y values, and so the x value on the coordinate plane, having x also stand for something different in the same problem, is problematic. I would suggest always changing that to a or b or whatever, but not x or y. So here, the important thing is this is an angle finding machine. Therefore, this is the cosine of an angle. Because I'm finding the cosine of an angle, I'll get one answer. Also, it says express algebraically in terms of a. So if sine of some angle equals a, and sine is y over r, then a must be y and r must be 1. So I can draw that out. I'll say the hypotenuse is 1. I'll say the y value is a. And I'll look for the x value. So x squared plus a squared would equal 1 squared. X squared would equal 1 minus a squared. And so x must equal the square root of 1 minus a squared. And so if I want the cosine of this angle, then the cosine is adjacent over hypotenuse, or this has to be just the square root of 1 minus a squared over 1. Similarly, tangent is, it's x, it's y over x. Y over x. So the y value is a, and the x value is the square root of 1 minus a squared. I could certainly rationalize that denominator, but this is enough for you to get the point that you can express trig functions out in terms of just straight up algebra just by using Pythagorean theorem and a triangle that you set up. The key is remembering that this is an angle. What else we got? Alright, so solving equations. One of the big reasons we learn inverse trig functions is to solve equations. So if I want to solve this equation for that angle, first of all, because I'm looking for an angle, I'm going to get an infinite number of solutions as we go around and around the circle. So what I want to do here, the key here, is to isolate the trig function. Alright, this one's really easy. I just got to get sine by itself. So I'll add 1. And so 2 times the sine of theta equals 1. I can divide by 2. So if the sine of theta equals 1/2, then theta equals the inverse sine of 1/2. In other words, what angle would I need to get a sine of 1/2? By now you should know that that's a 30-degree angle. 30 degrees, this is similar to the other problem. That's pi over 6. So one of my answers is going to be pi over 6 plus 2 pi k, where k is an integer. But there's another place that will give me a sine of 1/2. I just have to figure out where it is. Sine is positive here and here, because it's y over r, and that's where y is positive. Negative there and there. That means a 30-degree angle over here would also give me a sine of 1/2. And so how would I get to that angle? I would get to that angle with a 150 degree angle of reference. So 150 degrees, that's 5 pi over 6. And so I could also say that theta equals 5 pi over 6 plus 2 pi k. Those are all the solutions. K can be negative, k can be 0, as long as k is a whole number. How about this one? Where do the graphs of sine and cosine intersect? Now, if we take a look at this, this is the graph we were looking at before. The red graph is sine, the green graph is cosine. You can see that it like meets here, here, and here. In fact, you could probably see that really we could just figure out that spot and know that it's, you know, every period we're going to hit that spot. And the same thing is true down here. So maybe if we could just figure out these two spots, then we could do plus 2 pi k and we'd be cool. So let's see here. Ways to figure out this problem. Let's say that I've got a sine wave and I have a cosine wave. And I can easily think of this, in fact I usually think of this, as being in quadrants. You know, when sine is 1 and cosine is 0, that's the first quadrant. When sine is 0 and cosine is -1, that's the second quadrant. When cosine is 0 and sine is -1, that's the third quadrant. And of course, there's none to it. So you have 4 quadrants, 1, 2, 3, 4. And we're trying to figure out where they meet here and there. Now, Anna Bennett was all smarticles and her particles, and she said, look, this is the first quadrant. That's pi over 2. It meets halfway through. It's got to be pi over 4. Well done. How easy is that? There are a couple other ways to think about it, though. One is by thinking about cofunctions. Right? I know that sine and cosine are cofunctions. So if they're equal, their angles add up to 90 degrees. So if the sine of theta equals the cosine of theta, then theta plus theta, or 2 theta, has to equal 90 degrees. And so theta has to be 45 degrees, or pi over 4. And I could say pi over 4 plus 2 pi k, because that's the period of sine and cosine. So over here, in the 5th quadrant, we will have gone around the circle, and they should meet again. But there's also this point down here to think about. And the question would be, well, where is that point? And the answer you'd say is, it's in the 3rd quadrant. And of course it's in the 3rd quadrant. I mean, if we think about it like this, look. Sine is positive here, negative here, and negative here. Cosine is positive here, but negative there, and positive there. In order for the graphs to meet, they have to be equal. We figured out in the 1st quadrant it's a pi over 4. They can't be equal here or here because they're different signs. They've got to be equal here. And in fact, we can see that they're equal when they're negative. So this has to be in this quadrant. If it's in this quadrant, it's going to have to be an angle of reference of 45 degrees. We already know that. So it's pi over 4 as a reference angle there. If it's 4 pi over 4, this would be 5 pi over 4. So I could say 5 pi over 4 plus 2 pi k. That would make a 45-45-90 triangle, 1, 1, root 2. The sine of that angle is 1 over root 2. The cosine of that angle is 1 over root 2. They're equal, and the graphs are going to meet. These are the answers, but believe it or not, this isn't simplified. The reason it isn't simplified is because pi over 4 to 5 pi over 4 is 1 pi. It's 4 pi over 4, so it's 1 pi. So we could just say pi over 4 plus pi k. And we can get to that answer pretty easily if we solve this problem a different way, which is to say that if sine of theta equals cosine of theta, we could try to use an inverse function. we could try to like divide both sides by the cosine of theta. If we do that, then the tangent of theta must equal 1. In other words, theta would be the inverse tangent of 1. And we would ask ourselves, well, where does the tangent equal 1? And we would draw a coordinate plane and we would say, oh, we know that a tangent of 1 means the x value and the y value are the same. So this must be a 45-degree angle, or pi over 4. And then you'd say, okay, so the answer has to be pi over 4, but plus pi k. And the reason for tangent that we have pi k instead of 2 pi k is because if you think about what the period of tangent is, the period of tangent is not 2 pi, it's pi. The whole pattern repeats itself every half a time around the circle. So this is a better and more simplified answer, and it's equivalent to that. Okay, next problem. Let's say I have this. I'm trying to solve it. Well, one tip here is that having a 1 function would be better. Excuse me. So if having 1 function would be better, then you have to think, how could I change this? Now you might look at this and say, wait a second, we have a power reduction formula that we just uncovered last week. But the power reduction formulas would take cosine squared and turn it into a form that had just a regular cosine in it. That wouldn't really help us, because then we'd still have a sine and a cosine. But what you also might see is cosine squared. You might think, well, I know that sine squared plus cosine squared is 1. And if that's true, then I should be able to subtract sine squared and know that cosine squared equals 1 minus sine squared. If I do that, then all of a sudden I have an equation that's entirely in sine. Now I can't isolate it like this because these aren't like terms. One's squared and one's not. But what I should be able to do is think that sometimes I'll have to deal with quadratics. And that's what this is. It's a quadratic trigonometric function. And I know how to deal with quadratics. I'm going to set it equal to 0 and I'm going to solve it. So I'm going to add sine squared to both sides and subtract 1. And so what I have is the sine squared of theta plus the sine of theta equals 0. I can factor that. So the sine of theta times the sine of theta plus 1 would equal 0. And then I'll use the zero product property, like either sine of theta is 0 or sine of theta is negative 1. So now I can think of this. I can take this and I can think, where would that be true? Sine of theta is 0. Now you can draw a coordinate plane and do it all out that way, but I also like to just use the graphs. Like here's the graph of sine. Where is it 0? It's 0 at 0, pi, and 2 pi. In fact, it's 0 at pi plus pi k, like every halfway around the circle. In fact, you could just write that, pi k, and you would be right. Where is it equal to negative 1? It's equal to negative 1 down here. That's at 270 degrees, or 3 pi over 2. So I have that theta must be 3 pi over 2 plus 2 pi k. Those together tell us every solution for this problem. I think this might be the last one. Yeah. This is the last one. And the reason I threw this one up here is because sometimes you gotta go, like, I want to make cosine or sine, I want to make it all in terms of one function, but I don't have anything squared. So I don't have the kind of like nifty thing going on here where I can just use a Pythagorean identity. And so the idea here is that, you know, you got to make the equation be what you need it to be. So if I want squares so that I can use a Pythagorean identity, then just do that. Square it. You can square both sides. So if I square both sides, now I have cosine squared of alpha plus 2 cosines of alpha plus 1, and that would equal sine squared of alpha. I can use a Pythagorean identity and say that's 1 minus cosine squared. And now everything's in terms of cosine squared and cosine. So I can look at it as a quadratic. I can subtract 1 from both sides and add cosine squared theta from both sides. I do that, and all of a sudden this problem looks a lot like the last one. Cosine squared of theta, 2 of them, plus 2 cosines of theta for alpha equals 0. I can factor the 2 cosine alpha out, and from there use the zero product property. So either cosine of alpha equals 0 or cosine of alpha equals -1. Again, where's that true? It's 0 here and here. That's at pi over 2, and that's at 3 pi over 2. That's actually a distance of pi. And if I added another pi, I would get back to 0 again. So I'm going to say this is pi over 2 plus pi k. And where is cosine -1? It's -1 down here. That is at pi. So I'm going to say it's that alpha is pi plus 2 pi k. Because I'd have to go around the circle again entirely to get to another -1 value. And there you go. Those are all the solutions. So the key here is to remember that inverse trig functions are like a logarithm. A logarithm is an inverse exponential function, and it is an exponent finding machine. Inverse trig functions are just angle finding machines. So when you see something like that, you have to say to yourself, that represents an angle. And if you do that, I think you'll survive. All right, video over.